Okay, geometry, let's get rolling into section 1.3. And while 1.2 was kind of just an introduction to a lot of the concepts within geometry in a general sense, now in 1.3 we start talking about something a little bit more specific, and that is the concept of line segments and the fact that we're going to be measuring those segments within the section. So with a postulate, the way we do in a great many of our sections right here. And if you recall from our notes on 1.2, a postulate is a mathematical idea that we know to be true, but one that cannot be proven. We don't need to dwell too much on that second part. The important thing here is that we know that what we're about to talk about is a fact. And this is one called the ruler postulate that is incredibly important, but honestly, it's almost taken as a given, and I don't think you guys are going to spend a whole lot of time thinking about it. But the ruler postulate, if we just boil it down to something nice and simple, it essentially says that every line segment can be measured. Every line segment can be measured using something called a ruler. Okay, and a ruler is something I don't think we need to talk about in great detail, everybody, because you've been using it since probably about second grade. The good news for you guys is right now you do not need to go get your own ruler. We're not actually going to be measuring a whole lot of things out there. But just to make our point here, if we were to draw ourselves a line segment, and let me try to do this properly here, remember that a line segment has two endpoints and it consists of all of the points in between. I should probably draw this one horizontally here to make it easier to measure. So if I were to simply say one of these endpoints here is going to be point D and the other endpoint on the other side is going to be K, we can simply use a ruler now to measure the distance between points D and K. And so I'm going to use my smartboard ruler here, and probably the easiest thing to do, maybe I should have made that a little smaller, would be to set it up so that the 0 on the left-hand side of the ruler matches up with point D. And then we can simply read across and try to find out where that K is. Now it looks like on my ruler here, yeah, I did make this line segment a little bit too big, but it looks like that segment is maybe in the neighborhood of about 6 inches long. A slightly different way of doing it would have been something like this. Let me go ahead and draw another line segment that's shorter than the one that we started with. And instead of a D and a K, I'm going to call this point, how about Z? And then we'll throw a Y right over here. Now again, if I were trying to measure the length of line segment ZY, the best thing to do with it, that's not what I wanted to do, the best thing to do would probably be to put the 0 on the left-hand side of the ruler right at Z, and then try to figure out where we are with point Y. So it looks there, guys, like we're at roughly about 2 5/8 inches. But the other thing you could do, if you were so inclined here, is to move it around a little bit randomly here and see where those numbers end up now. Like for example, it looks like I've got point Z at about 1.5 inches on the ruler. So if I put a 1.5 right over there for the coordinate, if you will, of Z. Now let me go over here to Y, and it looks like Y is located at about 4 1/8 inches. And so if we wanted to measure the length of XY, one of the things that the ruler postulate says that we can do is simply subtract the ending coordinate, which is Y, take that number and subtract the beginning coordinate from that. So obviously this is a harder way to do it, but if we were going to take 4 1/8 minus 1 1/2, oh boy, we haven't done this kind of math in a long time. That's 4 1/8 minus 1 4/8, getting a common denominator there. We'd have to do some borrowing now. That 4, we'll take that down to a 3, and we'll add 8/8 to the 1/8 and get 3 9/8 minus 1 4/8, and that's going to get a distance now. The 3 minus 1 is 2. The 9/8 minus 4/8 is going to be 5/8, and that would be the distance there, everybody. Obviously, that was a dumb way to choose to do the problem. It would have been much easier if we had simply put the ruler with the 0 at Z and just read off the 2 5/8 that way. But the point is, it can be done in that regard. Now, I skipped right over this piece of information right here. There's a notation that we're going to use a lot here, everybody, this year, and it's one that you guys absolutely need to understand before we move any further. If you just see this symbol right here, AB, two capital letters with no symbol, not a line segment, not a ray. Two capital letters right next to each other. That notation means the distance between A and B. Or you could say, in fact, you know what? I actually would like that better. Let's do that as the measure of line segment AB. Okay, so with the symbol over the top, like I drew on the right, now we're talking about the geometric name of a figure. But when you just see right over here, AB by itself with nothing around it, that means the measure of line segment AB. So with this work that I did in red, I was trying to find the measure of line segment ZY. So really, this would be a proper way of writing that. ZY is equal to all of that work, and we end up then with this. And the way we would read this final statement, everyone, is the measure of line segment ZY is 2 5/8 units, whatever units it is that we're talking about there. So the ruler postulate is not incredibly practical for us. It tells us something that I think we all knew anyway, that you can measure a line segment using a ruler. I don't think we need to call NASA and tell them we just learned something new. But let's talk about how to do it in a problem a little bit more like what it is we're going to see on our homework. And what we have here, guys, is a one-dimensional space. When we talk about one-dimensional, we basically mean that these 3 points are all collinear. That's a word we were supposed to have learned in section 1.2, and I'm going to try to keep using it as much as we can so that we get familiar with it. Collinear points all fall on the same common line, and it certainly looks here like A, B, and C are all on that line. Now, specifically, this line is a number line, everybody. A is located at the coordinate of -8, B is -2, and C is 3. All right? And with that in mind, we're asked then to come up with the measurements of 3 different line segments. The first one being line segment AB, which from the name we know starts at A and goes until B and ends right there. Now, without actually pulling out a ruler and without sitting here and counting every single integer value in between, we're not going to do it that way, we're going to utilize that method for coming up with the measure of ZY, which was kind of silly to do available to us, but for now, it's what we're going to use. We're always going to take the ending coordinate of this line segment minus the starting coordinate, but we always want to go the one on the right here minus the one on the left. That assures us that our answer, by taking right minus left, or bigger number minus smaller number, that assures us that our answer is going to be positive. And that is something we always want for the measurement of a line segment. Okay, it's going to be impossible for us, and we're not going to want it to happen all year, that the measure of a segment comes out to be negative. So, to find the measure of AB, we take the coordinate of the right endpoint, which is B, that is -2, and we subtract the coordinate of the left endpoint, A, which is -8. So let me say that again. This is going to be -2 minus -8. So that's exactly what I'm writing there, -2 minus -8. But as I'm hoping you guys remember from pre-algebra and algebra 1, subtracting a negative is more easily understood as simply adding a positive, and -2 plus 8 is going to give us 6 for the measure of line segment AB. Okay, so that distance here from A to B is going to have a length here of 6. All right, so what's that saying, everybody? If we were $8 in the hole and we gained or made $6, now we're only $2 in the hole. Or as football season is starting here, if you lost 8 yards on the first play and now all of a sudden you gained 6, you're still 2 behind where you started, but hey, at least you're closer to it. Let's do the second example, the measure of line segment B. So it's the same concept now. We take the of line segment BC, which is now point C, and that coordinate is 3. We subtract the left coordinate of BC, which is now B, that's -2. So it's always going to be right minus left. So in BC, it's C coordinate minus B's coordinate, 3 minus negative 2. We could rewrite that as 3 plus 2, and that means we end up with 5 now for the measure of line segment BC. So it doesn't really look like my drawing is to scale, everybody, but that's not an assumption that we get to make just by looking at a diagram. And the last one here, everybody, this fundamental concept that with 3 points, A, B, and C, there's actually 3 line segments in this figure. Everybody sees the first one, AB, everybody sees the second one, BC, but there is, of course, a larger one, everybody, the whole segment that goes from A to C. That's a third line segment. And left endpoint. So the right endpoint of line segment AC, that comes from point C, which is 3, minus the left endpoint coordinate. Well, the left endpoint is A, its coordinate is negative 8, so we have 3 minus negative 8. The minus negative becomes a plus, and 3 plus 8, last time I checked, is 11. So we would read that as saying the measure of line segment AC is 11. And the one thing I want you guys to think of before we turn the page and move on right here, do these 3 answers make sense in relation to one another? And what I'm hoping you guys noticed already is that if we already knew that the measure of AB was 6 and that the measure of BC was 5, this answer right here of 11 really shouldn't surprise you, because 11 is the sum of 6 and 5. The big segment, AC, is made up of the sum of its 2 individual pieces, AB plus BC. And that becomes the segue for something we're going to move into here. So our second postulate of this section, again, a mathematical idea that we know is true even though it cannot be proven, is called the segment addition postulate. And unlike the ruler postulate, which is necessary but not really all that practically important as we move through, the segment addition postulate is one we are going to be using a lot, everybody. And the segment addition postulate says the following. Now, one thing you'll see me get into here, guys, most of our postulates and theorems and laws this year are going to be written in something called if-then form. Now, this is something that we normally cover in Chapter 2, although this year we're not going to be hitting that quite as heavily because we're de-emphasizing Chapter 2 with e-learning. But if-then statements generally consist of 2 parts. The beginning is called the hypothesis. If this happens. And the second part, the then, is called the conclusion. So the hypothesis here is if A, B, and C are collinear. And as you look at my diagram right here, you guys can see that I've drawn something that satisfies that hypothesis. I've drawn points A, B, and C, and I've made them all collinear points. Then, and this is what we would write together if we were in class, guys, the conclusion of this statement is what we said just a moment ago. If you've got a diagram that looks like this, there are actually 3 line segments. There's the first little segment, which is AB. There's the second little segment, which is BC. And then there's the big segment, which runs from A all the way to C. So we've got to get used to seeing 3 different line segments right there. And the segment addition postulate, well, the name kind of tells you what we're doing. We are going to add up segments, or better yet, we're going to add up the lengths of segments. This postulate tells us now if A, B, and C are collinear, then the measure of segment AB can be added to the measure of segment BC. Little segment, right here, plus little segment, right here, equals the measure of the big segment, which runs from A to C. So that right there, everybody, is our first real practically useful postulate here that we've covered in geometry. And as I said, we're going to use this one a lot throughout Chapter 1. If A, B, and C are collinear, then the measure of AB plus the measure of BC is equal to the measure of AC. But it only applies if the 3 points are collinear. Very quickly, you guys do not need to write this down, but if I drew 3 non-collinear points, like here's A and here's B, and then I put point C over here, well, I've just made a triangle there. And just guessing here, it's possible that the lengths of the sides in that triangle could be 5, 6, and 7. Then the statement we just wrote down, AB plus BC equals AC, is not true in this case. The measure of AB is 5, the measure of B is 6, and the measure of AC is 7. This is absolutely a false statement right here. It doesn't work in this case because the hypothesis of the postulate was not satisfied. The hypothesis of that postulate said that A, B, and C had to be collinear. Well, as soon as you can create a triangle between 3 points, they are not collinear. So the segment addition postulate only works when your 3 points are collinear with one another. So we've got to be careful about what people do a lot is they ignore the beginning of the postulate, the if-then statement, and they only focus on the second part. And that's a really important mistake that we want to make sure that we avoid. So let's take a look at our first example here, everybody. We're going to try to find x in this diagram right here. And a lot of you can look at this problem and already know what the answer is, but we want to try to be systematic about this because the problems are going to get harder. And for those of you who can rely on mathematical instinct to look at this and say, oh yeah, x is 6, good for you, but then when you get to harder problems like this one or this one right here, that mathematical instinct is not going to help you. So you've got to train yourself to slow down a little bit and do this in a process that's repeatable from one problem to the next. So what's going on here, guys? We have 3 points, and I didn't label them, but let's call them M, N, and O, and those 3 points appear to be collinear. And collinearity is something we are allowed to assume from a diagram. Therefore, since the points are collinear, this postulate, the segment addition postulate, applies. If A, B, and C are collinear, then the measures of the 2 little segments add together, and that equals the measure of the big segment. Or as I always like to say, little segment plus little segment equals big segment. If you wanted to nerd this up here, guys, what we could do is write something like the first little segment here, which is the measure of MN, and add that to the measure of the second little segment, which is NO, would equal the measure of the big segment, which is MO. But this is a step right here, what I just wrote, that most people skip, and most people go directly to the diagram and start putting in values. What is the length of the first little segment right here? That one is 11. That's the measure of MN. Plus, the measure of the second little segment from N to O, that's unknown, so that's X. And then the measure of the big segment from M to O, that's this 17 that's written down here on the bottom. And now, everybody, we're starting to realize, and we'll realize this a lot, why geometry has to come after algebra and not before. You need algebra to solve the equation that you've set up here geometrically. So, of course, we're going to subtract an 11 from the left to get x by itself and do the same thing to the right to balance that out. And sure enough, we get x equals 6. And that is what we were asked to find there. This is something I always want to go back to and look at. Make sure you go back and read your directions again before you think you're done with a problem, and make sure that you have answered the question that they asked. And sure enough, they said find x, and we found that the value of x would be 6. Okay, so that was one easy example that I think a lot of you were able to do in your heads, but right here, not so. Though, it's the exact same concept. We've got 3 collinear points here, here, and here. And if you have 3 collinear points, then the segment addition postulate applies. Little segment plus little segment equals big segment. The measure of our first little segment is 3x. We're going to add to that the measure of our next little segment, even though it's pretty big, which is 7x minus 4. Now, if you want, really, putting parentheses around that because it represents one segment isn't a bad idea. We're just adding, it's not necessary. So, in fact, let me get rid of that. Little segment, ooh, that was weird. Little segment plus little segment is equal to, and the measure of the big segment here is going to be 26. This one's a little bit more complicated than what we did before, simply because we have a little bit of algebraic simplification to do on either side. But one thing I want to encourage you guys to do this year, now that you've graduated past Algebra 1, if you can start to do two things at once, let's try to do that if we can. For example, I've got like terms right here that can be added together, but at the same time, I think we can get rid of that -4 by adding a 4 on the left. Same number over here on the right. So those 4's are going to cancel. And now on the left side, we're left with a 3x plus a 7x, which I think you guys can handle mentally, knowing that that's going to be 10x. Over on the right side, 26 plus 4 is going to give us 30. And then from here, we just need to divide both sides of the equation by 10, and that's going to get us x is equal to 3. Now that is what I think my answer is. The question did say find x, or better yet, it should say solve for x. But one of the habits that I want you guys to get into this year, that I know you've been told in the past, but people just ignore all the time, is to check your answer before you move on. And guys, I've got to tell you, the students that learn to do this, who can stay disciplined enough and take the 10 seconds that this might take, those are the students who end up doing well in geometry. Students that don't do this very often get wrong answers and don't know it and end up not doing very well at all. So let's take just a moment and see what happens when we assume that we're correct, that x is 3, and we plug that 3 back into the original diagram. Right here, guys, this first little segment is 3x, which means 3 times 3, and that gets us a measurement of 9. Now that doesn't tell us anything, but I got to keep going. How about the second little segment, 7x minus 4? So again, we believe that x is 3. So 7 times 3 is 21, and 21 minus 4 is going to get us 17. Now if we take a look at our two individual pieces, 9 for the smaller one, 17 for the larger one, if we add those two together, 9 plus 17, sure enough, gets us 26, which is the measurement of the entire segment. So now I feel even more confident in that answer, and now I'm going to go ahead and box it up before we move on to the next problem. So seriously and legitimately, checking those answers is probably not going to take you more than 10 to 15 seconds per problem, but that's something you guys should really force yourselves to do before we move on here. And let's try this one last one, which is a little bit more complicated than the one that we just did, because we have variables in all 3 spots now. But yet again, ask yourself what we have in the diagram. 3 points, D, H, and S, which are all collinear. And if those points are collinear, all on the same straight line, then the segment addition postulate applies. Little segment plus little segment is equal to big segment. So here we go. The measure of the first little segment from D to H, that's going to be 4x minus 3. We're going to add to that the measure of the second segment from H to S, which is 2x plus 5. So little segment plus little segment equals the measure of the entire segment from D to S, which is represented as 8x minus 4. So as I said, it's really the same concept as example B that we just finished, except now there's variables on the right side as well. Let's combine some like terms, everybody. 4x and 2x is going to give us 6x. A negative 3 combined with a positive 5 is going to give us a plus 2. And you can't do anything with the right side for now. That's going to stay 8x minus 4. At this point, everybody, we need to make a decision about which side to bring our variables to and which side to bring our constants to. I always like to think about variables first, and the simple rule to follow is to move the smaller variable term towards the bigger one. 6x is the smaller variable term, so we're going to move that by subtracting a 6x from each side. And if I were your Algebra 1 teacher, I would tell you to only do one thing at a time and then work on the constants on the next step. But at this level, guys, to be honest, we're concerned with efficiency. If we're moving all the variable terms to the right, that means we also want to move all the constant terms to the left. And so for that reason, I'm going to go ahead and take this -4 over here on the right, and I'm going to move that to the other side by adding 4 on the right and balance that by also adding 4 on the left. The important thing here is, guys, we're doing the same thing on both the left and the right side of the equation. On each side, we're subtracting 6x and adding 4. Now that allows us to kill 2 birds with 1 stone. The 6x's on the left cancel, the 4's on the right cancel, and let's see where that gets us. The 2 plus 4 is going to be a 6 here on the left. 8x minus 6x is going to be a 2x on the right, and now we simply need to divide both sides by 2, and we'll get x equals 3 for our solution. Now, you'll notice that I laid this one out for you here, guys. I asked not just to find x, although we believe we know that x is 3, but I also asked you to find the measures of all 3 line segments built in here. This is something I do for you guys a lot on quizzes and tests, and you're welcome for it, everybody, because it's a built-in check. We should be able to look at the 3 numerical values that we get for these next 3 questions and make sure they all fit together. Let me show you what I mean. dH, everybody, the measure of dH is 4x minus 3, and we believe we know that x is 3, so let's check that. 4 times 3 is 12, and 12 minus 3 is going to get us 9 for the measure of dH. Let's move on to HS. HS is 2x plus 5. So 2 times 3 is going to get us 6, and that 6 plus 5 is going to get us 11. And actually, I like this problem, even though I think I might have done something a little bit wrong when I made it. And the reason why is this. A lot of people look at this diagram and they say, wait a minute, Mr. Fontana, you must have messed something up, because you just said that DH on the left side here, was 9. Then you said that HS on the right side was 11, but clearly this piece is longer. So that 9 right there can't be right. It's got to be bigger than the 11. Well, what I need to tell you guys at this point is that while there are certain things that you're allowed to assume from a diagram in geometry, like for example collinearity, one thing you are not allowed to assume is a hierarchy of lengths here. You can't look at this diagram and know for a fact that DH is longer than HS. You've got to go with the numerical information that's presented to you. So even though it doesn't look like it, everybody, HS is longer than DH simply because 11 is bigger than 9. And let's go back and check this last one right here now, everybody, the measure of DS. So that's 8 times 3, which is 24, and 24 minus 4 is going to get us 20. And I said this would be a built-in check. If you look at your 3 segment lengths right here, we've got 9 plus 11, which sure enough equals 20. So I feel really confident in those answers right there because I got the answer algebraically for x being 3, and then my segments all added together at the end right there. But notice, guys, what I didn't do to come up with the measure of ds, oh, that was weird. What I didn't do, there we go, is simply say, okay, this is 9 and this is 11, so let me add those together and get 20. That's kind of a prophecy right there, everybody, that wouldn't have told us if we got the right answer. So we actually plugged the x back in here and got that 20, and now I know for a fact that those answers are correct. Okay, so moving right along here. All right, we now start talking about a word, everybody, that gets used a lot in geometry, and I'm not sure how much you've seen it in the past, and that word here is congruent. All right, and when we talk about congruent segments, that applies specifically to this setting. So the word congruent is really a geometric word that I'm not sure you guys have heard before, but it says the following, everybody. Congruent simply means 2 geometric figures that have equal measures. Having equal measures. That's probably the simplest way that we can put it here in geometry. So congruent segments then, I think we can figure out, would be 2 segments that have the same measure. Okay, so if we wanted to draw two congruent segments, I could draw one of them here, and I'm just eyeballing this, so this might not be perfect, everybody, but let me call that line segment AB. Actually, you know what? I'm going to cheat here. I'm going to clone that line segment, and when you guys see me clone something on the smartboard, I'm even going to flip it just a little bit. That's like an automatic paste right there. But I've got to change the names of these 2 points. You can't have two different point A's and two different point B's, so let me call that point C and that point D. And if I did this right, everybody, those two line segments should have absolute length to them. So our notation here would be the following. Line segment AB, and since I said line segment, I've got to put the segment symbol over the top, is congruent to line segment CD. So here's line segment CD, and the symbol for congruent, I'm not sure if you guys have seen it before, is an equals sign with like a little tilde right over the top, everybody. That is the notation right there to say that segment AB is congruent to segment CD. And again, congruent means that these two line segments have the exact same measures. Now, one little notation we use in geometry a lot, guys, you're going to see this a ton really throughout the entire year. If two line segments in one diagram are congruent, we use the same number of tick marks to show that they're the same length. For example, I could put one tick mark here on line segment AB and one tick mark here on line segment CD, and that tells me that those two segments are congruent. Or we could put a double tick mark on AB, and now we would need a double tick mark on CD. But the same number of tick marks on each segment indicates that those two segments are congruent. Even if they don't really look like it, guys. If I gave you a diagram with one segment that looked like this and one segment that looks like that, I think we would all agree that the second one I drew looks longer than the first one. But if they both have one tick mark there, we're not allowed to trust our eyes. We have to go with the information presented to us and know that those two green segments are congruent even though they don't really look like it. Okay, so that's the definition of the word congruent and the notation going along with it. All right, little bit more definitions right here that we need to talk about. The first word I wanted to talk about was midpoint. And the word midpoint is one that if you think about, you can probably break it down into its two parts. It is a point in the middle of a line segment. So the formal definition here, guys, a midpoint is the point B located on line segment AC that divides segment AC into two congruent segments. And there's that word congruent that we just talked about, meaning having equal measures. So if I'm trying to figure out what to draw right here, I've got to draw a point B that's located on a line segment AC. I'm actually going to start with AC. So here's point A. I'm going to draw a line segment going over here and say, okay, that's point C. So we've created line segment AC. There are an infinite number of points that are located on line segment AC, but only one of them cuts AC up into two equal or congruent segments, and that, I'm just eyeballing this here, guys, but that is probably located right about here. So point B then would be the midpoint if it created two congruent segments. How do I show two congruent segments? Tick marks, everybody. Line segment AB is congruent to line segment BC. And now, in that diagram, I know that B is my midpoint. Why? Because B is on segment AC, they're all collinear, and AB and BC are congruent to each other. Now, another word that goes along with midpoint, but is actually a slightly less specific version of that, the word bisector. And if we think about what that word means right there, to bisect something, well, the word sect right there means a portion of something. And the prefix bi means two. So a bisector is something that cuts something into two equal parts. All right, so a bisector can be multiple things. It can be a point, it can be a line, a segment, or a ray, but what's really important is what it does. It divides a segment or an angle, we'll get to that later in this chapter, into two smaller congruent points. parts, excuse me. So what we could say, back to this diagram, is that B bisects line segment AC. That's a simple, true statement right there, guys. B is a point on AC that cut it into two smaller congruent parts. So there's really two ways of saying this. B is the midpoint of line segment AC using this definition, but you could also say that B is a bisector of line segment AC. Both of those things are true. Now, what you'd want to be careful of would be this. Don't put this in your notes, guys, but if I made a line passing through point B and called this point Z right here, you could now say, using this definition, remember, a bisector can be a line. So we could say that line BZ, in fact, let me go ahead and write that out. You guys don't have to, but line BZ also bisects line segment AC. It cuts it into two congruent parts. But you would not be able to say that line BZ is a midpoint of AC because a midpoint must be a point. A line can't be a midpoint. Okay? And I think we are just about done here, guys. I think I had one more problem that I wanted to do with you guys, and I think that's it after that. Let's knock this one out real quickly. Okay, so I felt like talking about the Cubs on this one here, guys, so let's see where we're at with this. All right, so this is the diagram that we've been given, and it looked a little bit like some of the problems that we were doing earlier in the day, but, well, that's weird. Things aren't working right there. Looked a little like a segment addition postulate problem, except I never told you guys what the length from C to B was. So if you thought about this as little segment plus little segment equals big segment, you're not wrong. The problem is the big segment, CB, we don't have a measurement for, so there's no way to solve this equation. So as fun as that was, that is not going to be the way that we're going to go about this problem. Instead, we're going to take advantage of something that wasn't given to us earlier, and that is the tick marks that are given to us on line segment CU and line segment UB. So going back to what we wrote just a moment ago, the tick marks tell us that CU and UB are congruent to each other. And the definition of congruent means having equal measures. So that means that this distance from C to U, which is 8 minus 3n, and this distance from U to B, which is 24 plus 5n, those two lengths or measurements have to be equal to each other because the tick marks tell us that. 8 minus 3n must equal 24 plus 5n. All right, let's get all our variables on one side. The smaller term is the negative 3n, so I'm going to add 3n on both sides. And just like last time, since all of the variables are moving right, all of the constants are going to move left. We're going to subtract a 24 from both sides. And I believe something weird happened here, and I think I did it on purpose. Those terms cancel, those terms cancel. 8 minus 24 is going to leave us with a negative 16. 5n plus 3n is going to be 8n. We're going to divide both sides by 8, and we're going to end up with n equals negative 2. Now in Algebra 1, you wouldn't have thought twice at all about that answer. You get negative answers all the time. In geometry, it's much more rare to get a negative value for your variable. And a lot of times people think that that's not possible. Here's what we need to say loud and clear. It is possible in geometry for your variables to end up negative, but what's not possible is for the length of a line segment or the measure of an angle to end up negative. You can't have a line segment, everybody, that's negative 5 inches long. It just doesn't make any sense. So we need to make sure now that when we use this value of negative 2, we need to make sure, everybody, that it's going to give us positive results for the 3 segment lengths. So let's try that real quick and make sure it works out. CU, everybody, is 8 minus 3n. So that's a negative 3 times negative 2, which is positive 6. 8 plus 6 is 14. Okay? IUB now. 5 times -2 is -10, and 24 plus a -10 or 24 minus 10 is 14 also. That makes me feel really good about this answer, guys, because of the tick marks that we saw here and here telling me that these two segments should be congruent. And unfortunately, to find the measure of CB, I have to make the assumption that what I did before was correct. I don't know the overall measurement of CB to be able to plug back in, so now we've got a segment addition postulate and say little segment plus little segment equals the big segment. That means that CB would have to be 28. There's really no way of verifying that, everybody, but we're just going to have to assume that that one is correct. All right, everybody, that is a wrap on section 1.3, so let's give that homework a try, and if you have any questions, please let me know.